Swayam Prabha. Digital India. Educated India.
Okay, dear students, so today I will teach you again the enhanced electrocatalytic activity of the electrode surface and then how those enhanced activities we can use for biosensor development. So last class I think you already understood how we can make a highly catalytic active surface or enhanced surface by using different treatment, that is called tuning, that we can use for thermal treatment, electrochemical treatment, chemical treatment. I taught you last class just chemical treatment. Now I just come to example how we can use this chemical treatment, for example sodium borohydride treatment, for development or for design a biosensor. Let's come. So today mainly I will cover sodium boride treatments applications for biosensing applications, for biosensor development. So main keywords for this, if you want to search, also if you can check the sodium borohydride treatment for biosensors, for ultra sensitive biosensor development by using different chemical treatment, that also can be a good keyword for this topic, and enhancement of the signal, because this treatment definitely is helping to improve the signal to background ratio and you may get a ultra sensitive biosensor, right. So let's design a ultra sensitive biosensor by using this method. So why we are learning this chemical treatment, why we are learning this enhancement, let's use these applications for a biosensor development. Okay, let's see here a detection scheme. What detection scheme this one? This is just a DNA detection. Means similar like the antigen antibody I told you, and instead of using a antibody on the sensor surface, we are using capture DNA. This is called capture probe. Similar way, your capture DNA that can be modified with the biotin, biotin modified, something like that, similar like your antibody modified, conjugated with the biotin like biotin antibody, similar like this. So your surface is already avidin or streptavidin coated. It can be avidin or streptavidin coated, and just dendrimer is helping to bind this kind of they all are the linker basically. They are helping to bind this streptavidin or avidin on the surface, and your capture probe already biotinylated, right. That's why your capture probe already on the surface. Okay, now see, you are adding your target solution, DNA solution. So this is the target DNA. Suppose like the antigen in a solution, if you have some protein like target, as I was saying now. So here as for target you are using DNA, nothing, there is no difference. Just for before we use antibody antigen interactions, here we are using just DNA interactions, capture probe target DNA. Now on this target DNA, as for example we use last time secondary antibody, here we use a secondary that is called detection probe. This is for the DNA case, this is called detection probe, and that is also conjugated with gold nanoparticle, right. Last time like the secondary antibody can be conjugated with gold nanoparticle, and here detection probe also can be conjugated with gold nanoparticles. Okay, so your biosensor already developed on the sensor surface, clear. Now these gold nanoparticles can be used for the signal amplifications. How? We can apply that sodium borohydride treatment method that I taught you last class. See, if we activate this gold nanoparticle with sodium borohydride, then its catalytic activity will be improved. See, suppose for example last time I told you that you have the primary antibody and you have target antigen, secondary antibody, that secondary antibody conjugated the gold nanoparticle. This is just your like labeled antibody. So if this level is highly active, then definitely it will produce some electrochemical active product, and they can easily oxidate on the surface. And if this process kinetically very fast with the level, substrate and product formation, if it is kinetically very fast, so definitely your reactions will be very fast. You will get the high electron transfer rate and you will get the high signal, right. That is why we need to improve the electrocatalytic activity of this level gold nanoparticle. You may ask why I should improve, right. That is why. Here we use hydrazine just for example a substrate. So, hydrazine oxidation on your biosensor surface. So, at the beginning when your gold nanoparticle was not activated by sodium borohydride, that time activity was very low and you may get the very low signal. This is before sodium borohydride treatment, before NaBH4 treatment, and after the treatment, you are getting here. So, it means this signal means your hydrazine oxidation signal will be improved. Okay. Now, I will show you the problem of the gold nanoparticle based sensor. So, you may ask me, say, just you told the gold nanoparticle sodium borohydride was very good, then now you are asking it is a problem. Definitely, we need to further improve the electrocatalytic activity of the sensor surface. Yes, when we are using the gold nanoparticle, there is some drawback. Let us show you the drawbacks using the gold nanoparticle. Then we can further improve the catalytic activity or sensitivity of the biosensor by replacing gold nanoparticle with other nanoparticles. So, that this kind of research actually going on, that we are replacing one nanomaterial to another nanomaterial. That is why you will have some lots of scope to work again, like gold nanoparticle, there is some problem, we replace another nanoparticle, I will show you right now. Then maybe you can think about some other nanomaterial. That is why we have lots of scope. See, when you use these activations with the sodium borohydride, just I showed you in the last slide, and hydrazine oxidations, and in this case the problem is we need a long incubation time. How long? You need at least 15-minute incubation. So, you have to dip your sodium borohydride in this sensor surface for 15 minutes, and your pH of the solution should be less than 7. Your pH should be less than 7. Then only you will get the higher activity, electrocatalytic activity of this gold nanomaterial. This is the true problem, because if we use high pH like pH 7 or more than 7, 8 or 9, in this case one thing you can see, this activation rate is very slow for the gold case. So, this is the one pH factor, but if you decrease the pH for the gold case, another problem, sodium borohydride may decompose very fast by evolving the hydrogen gas. So, slowly its concentration can be changed with time. This is not a good factor if you decrease the pH. So, gold like low pH, but in the low pH sodium borohydride can be decomposed fast. And another problem for the gold case, it needs long time reaction, at least 15 minutes or more than, or 30 minutes. So, this is the two problem we can solve by using another nanomaterial. That is why we need some another nanomaterial. So, your detection probe, your DNA detection probe, which is already conjugated with gold nanoparticle, that we can replace some another nanoparticles. So, the question mark is which nanoparticles we can now use, right. So, let us these questions now we have, why not use one step, I mean instead enhance the sodium borohydride, and this sodium borohydride reactions actually can be slower rate for the gold, and another problem is the self hydrolysis, that's why the concentration of sodium borohydride with time can be decreased and you may not get very reproducible data. So, this problem can be solved by using another nanomaterial that is called palladium. Why just you say why I suddenly choose the palladium? Because palladium has this kind of properties. So, it can absorb the hydrogen very fast. When in the gold case he used just 15 minutes, and in this case 1 to 2 seconds only is enough for this hydrogen adsorption, because this hydrogen adsorption only is the cause for surface reconstruction. I think you remember this surface reconstruction. That's why we are getting the highly catalytic electrocatalytic surface. Now, if this hydrogen can adsorb very fast on your surface, then no need to go for the long time incubation. So, for the gold case where you use the 15 minutes, now we can go just 1 to 2 seconds if we use palladium nanoparticles. And this very fast hydrolysis of the sodium borohydride, that also we can stop by using higher pH. So, in the palladium nanoparticle case, we will use the pH more than 7 or around 7. So, in this case we can avoid the decompositions, and electrical activity also will be increased very fast. So, let us come on example. See here. So, when we measure a cyclic voltammogram, suppose this is just we measure just after treatment of the sodium borohydride, for example, a 50 millimolar sodium borohydride of gold nanoparticles, and we checked this is just a oxidation of hydrogen. Suppose we are measuring the hydrogen oxidation N2H4 hydrogen oxidation we are measuring. See, at the we are optimizing different time and oxidations of gold with sodium borohydride treatment. Okay. And we use the pH at the 11, high pH we use, more than 7 as I mentioned, because at the high pH the decomposition of sodium borohydride will be slow. See, we tried 3 seconds, we tried 15 seconds, we tried 30 minutes at the high pH. So, 3 seconds, 15 minutes, they are still not much improved. We tried after 15 minutes, 30 minutes, it is improved, but not that much. So, in the gold case, if we decrease the pH, it is like less than 7, then it can be improved very fast. But in the high pH, as I mentioned, it will not be improved very fast. See, after 30 minutes also it is not improved much. See, now we use the palladium. Your DNA that conjugated with the palladium nanoparticles. So, again now we started the optimization different time. See, this is the red one. This curve just after 3 seconds, just 3 seconds we measure, we got very high catalytic activity. See, here in this case how much current we are getting? Just 1.2 microamps. And here after 3 seconds we are getting like 320 microamps, right. So, this much high current we are getting. See, where is just 1.2 and here the 320 microampere. So, this much high amount of current we are getting using palladium nanoparticle just after 3 seconds. Now, we are checking after 3 seconds and again 15 minutes incubation. See, after 15 minutes sodium borohydride treatment, see they are showing almost the similar current. So, it means we do not need long, it is almost saturated after 3 seconds itself, means just deep, and sodium borohydride treatment will be very effective for palladium nanoparticles. That is why it is depend on nanoparticles to nanoparticles. So, this behavior now we can use for a biosensor development. So, as I showed you that gold nanoparticle case just like 1.2 microampere current increase, but palladium case 320 microampere current increase is how like 320 by suppose 2 microamps. So, how much? 160 times, right. So, this much current actually improved. So, definitely, so if we conjugate your detection probe with the palladium nanoparticle and improve the electrocatalytic activity by sodium borohydride, then think how much signal to background ratio you can improve, right. So, you can see here we modified a IIT. Now we are designing a biosensor by using this palladium nanoparticles. A ITO electrode that we modified is silane copolymer. This is just a copolymer. So, another way we can modify the sensor surface, something like APTES. You can search. This is kind of the name of this polymer, and we can modify like primary antibody or capture DNA. This kind of capture like who are helping to bind the target, those molecules we can modify. So, for the DNA case capture probe we modified on the sensor surface by using a silane copolymer. See, then we drop the target DNA, and they already attached on the capture probe. Now, we add the detection probe. This detection probe now conjugated with palladium nanoparticles. See, now this catalytic hydrolysis hydrogen adsorptions will happen very fast because of this sodium borohydride treatment, and we use here palladium nanoparticle. That is why this first phenomena we can observe. Now, let us observe. Now, let us check your electrocatalytic activity. You can use here, see, in this scheme we use sodium borohydride itself as substrate. Like last time we use hydrazine, right, N2H4 as the substrate oxidation, right, on the sensor surface. Here what is the new modification we did? This is a kind of the design of the sensor, right. So, you can select different chemical, like which chemical you can add for the substrate. Last time hydrazine you add as a substrate. Here we use sodium borohydride for activations. Again we use sodium borohydride for as a substrate, so that it will show this chemical, like how the electron transfer on the surface. So, basically sodium borohydride is actually oxidizing on your surface, and you are getting this output by measuring this electron transfer. See, so in this case, as sodium borohydride current, oxidation current we are measuring, it will show very fast oxidations of the sodium borohydride and fast catalytic hydrolysis of the NOBH4 and fast hydrogen adsorption. Everything will happen because we use the palladium nanoparticle. And one important thing, here we use pH around nearby 11, means high pH. So, hydrolysis of sodium borohydride also very low. So, we can avoid the reproducibility problem also. Last time we cannot use sodium borohydride as a substrate because last time we used the low pH. At that low pH sodium borohydride can be hydrolyzed, so concentration time by time also decrease. So, it can affect on reproducibility, but in this case as we use the pH 11, high pH, at that high pH it is very stable and we will get the reproducible data, and at the same time very high electrocatalytically active nanomaterial surface. Okay. Now, let us come here the detection limit. So, our biosensor already done, right. So, this is just a schematic, this is your sensor surface, you have capture probe and then you have your target already bound on the sensor surface. Now, you have the detection probe that already conjugated with palladium nanoparticles. Now, see, slowly you are increasing the target concentrations. So, I am telling about the calibration. This is calibration curve, right, you know, calibration curve. See, now if we increase the concentration of target DNA, we are increasing the concentration of target DNA. When it is like very small number of the target, then number of palladium also on your sensor surface is very low. Now, when you increase the target concentrations, like you have the many capture probe, so many target will come, and then many second like your detection probe will bind, so many palladium nanoparticle will come on the sensor surface. So, basically more number of palladium nanoparticles means you will get higher and higher current. See, even this very if you have very low number of the target concentrations, and if you have very low number of the palladium nanoparticle surface, because of the highly active, still you can detect the current, because very fast catalytic activity is showing, right. If you see now, here on calibration curve we measure, like with target DNA, we measure 10 attomolar, then we can see the difference. See, this is the background current. Background means just with the capture, means just a sensor surface. Then no target DNA. When you do not have any target DNA, then we are getting this much current. This is the cyclic voltammogram. And here actually we are showing only one oxidation curve. There is no reduction curve, only oxidation curve of the sodium borohydride. Okay. So, just background, just background means you can say that with the capture probe, then we checked with no target DNA and with 10 attomolar, very low concentration of target DNA, and we can see the difference of the current. Okay. So, if you see in this potential, we can differentiate the target concentrations. Now, if you further improve like 10 attomolar to 100, then if you see to the femtomolar, then to picomolar, then if you see, then you will get very high current difference you can see. So, if you see here the calibration curve, see the current, there is a change of the current, and now you please at the very low concentrations in the insert you can see all the low concentrations we put, and 3 times standard deviations that we measure, that we obtain because to calculate the limit of detections, right. You can remember what is the limit of detections. Limit of detections means how the lowest amount of the target you can detect. Okay. So, lowest amount of the target, if you like 1, 2, 3, 4, this like 4 points if you put, then they looks like a straight line. Although all the points if you put, they not all the straight line, but if you put these few points at a very low concentration, you will get the straight line. Now, 3 times standard deviations you see here, and now if you draw a straight line with these few concentrations and this 3 times standard deviation line, the intercept is this one. So, this limit of detection is almost 10 attomolar. So, it is very ultra sensitive, this biosensor, ultra sensitive. So, why it is possible to that much very low detection limit? Because of this your palladium activity. If you not add the sodium borohydride, if you go back here, see. So, if you without sodium borohydride, if you go up to this stage, so then maybe you may get some detection limit maybe in the picomolar range, because it may show the current if you go back here, see, without sodium borohydride treatment, maybe if you see the current may be very low in this range, but after the activations you are getting the very high range. So, this happen as we add the sodium borohydride. So, this chemical treatment we use for the ultra sensitive biosensor to get very low limit of detections. So, these things you have to remember. Not only the design of the sensor surface, also some treatment also can improve the further of your sensitivity of the electrochemical biosensors. Okay. So, these things actually we learned today, that how we can enhance the activity of the electrode surface, and this kind of enhancement can be done by very simple chemical that is called the sodium borohydride, and this tuning also can be done not only the gold, also we can use some other nanomaterial like palladium. So, and also you have another scope, just think maybe other nanomaterial also can be used, and this treatment also very simple, and we need just 1 to 3 like few seconds only, and enhancement can be done. So, this all the tuning method I taught for biosensing design. Next class again I will teach you some other enhancement method, and then apply those enhancement or those tuning, those pre-treatment. As I told, this method like chemical, electrochemical treatment, thermal treatment, this is kind of pre-treatment method. Those treatment also can help for further enhancement, and I will show you different design of biosensor based on all these pre-treatment design method. Okay, thank you for today.